Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we introduce polynomials. So what is a polynomial? Well, a polynomial is an expression of this form. So this is probably going to be a bit complicated at first, but don't worry, we'll go through what it means. So it is an expression with a pronumeral x and coefficients a0, a1, and so on. What makes this expression a polynomial is that the powers of x, the pronumeral, are all non-negative integers. So 0, 1, 2, 3, 4, and so on. Polynomials are really important because they have really nice properties that we will investigate in subsequent lessons. In fact, they're so good, we often approximate things by polynomials. For example, the cos and sine functions that you use in trigonometry, your calculator uses a polynomial to come up with their values. So this might still not be making a whole lot of sense. So let's look at some expressions and determine whether or not they're polynomials. So to determine whether or not expressions are polynomials, we follow this rule. The powers of the pronumeral, usually x, must be non-negative integers. So for example, any quadratic that we've gone through is a polynomial. X squared plus 4x plus 4 is an example of a polynomial. So we have our pronumeral x, we've only got non-negative powers of it. So we have power 2, power 1. Now 4 is the same as 4x to the power of 0. So the powers here are 0, 1, and 2. That is a polynomial because the only powers of x are non-negative integers. So something like this. 4x to the power of 5 minus 3x to the power of 6 plus x. That is a polynomial. The powers of x are 1, 6, and 5. They're all non-negative integers. So let's look at examples of things that are not polynomials. So these get the big tick. If I have something like the square root of x, well, you know square root of x is x to the power of a half. This power is not an integer. It's not a whole number. So this is not a polynomial. In fact, anything with that wouldn't be a polynomial. If we had something like 4x squared plus x minus the square root of x, that's not a polynomial because of the root x term. Similarly, if we have something like 5 over x plus 1, it's not a polynomial. Why? Because 5 over x is the same as 5x to the power of negative 1. And of course, negative 1 is a negative integer. So to be a polynomial, the pronumeral can only have non-negative integers as powers. So let's look at some definitions surrounding polynomials. So on the screen, I've defined two polynomials, one in blue and one in black. So the first polynomial, we usually call them like f or g, and we put in brackets what the pronumeral is. So we read this as f of x equals x cubed minus 2x squared plus 1. And then the one in black, g of x equals 2x to the power of 5 plus x squared minus 9. So both are polynomials because they have only non-negative integers as powers of x. So we just need to get some terminology right. The degree of a polynomial is the highest power of the pronumeral, which is usually x. So in our examples above there, the degree of f is 3. So f is a degree 3 polynomial, meaning it's a cubic, and the degree of the polynomial g is 5, because the highest power of x is 5, whereas in x it was 3. Okay, so we've done heaps of work with quadratics. They're degree 2 polynomials, because the highest power of x is 2. So like x squared plus 1 is a degree 2 polynomial. So the leading coefficient is the coefficient of that highest power of x. So for f, the leading coefficient is 1. The coefficient of x cubed is 1, so that means f is monic. Now for g, its leading coefficient is 2. The coefficient of x to the power of 5 is 2, so g is non-monic. I know we've seen these terms before. So monic polynomials have very special properties. They're just easier to work with. So monic means the leading coefficient's 1, and non-monic, the leading coefficient is not 1. So in f, the leading coefficient was 1, and in g, the leading coefficient was 2. So now we're going to look at performing operations with polynomials. So it turns out if you add or subtract or multiply two polynomials, the result is another polynomial. So let's start by adding these polynomials together. So if I take fx and add it to gx, all I need to do here is add the like terms. You know how to do that. So for gx, there's a 2x to the power of 5 term. For fx, there's an x cubed term. The like terms, we have minus 2x squared plus x squared. So that will give us minus x squared. And the other pair of like terms is 1 plus negative 9, which gives you minus 8. When adding or subtracting polynomials, you simply add or subtract the like terms. So for fx minus gx, so we have f, which is this, minus g. So we need to put this in brackets. So what we'll end up doing is just subtracting the like terms. So the x cubed doesn't have a like term. So this becomes a negative 2x to the power of 5. We leave it alone. So the x squareds are once again like terms. So minus 2x squared minus x squared gives you minus 3x squared. And then we have 1 minus 9. So it's 1 plus 9, which is 10. So adding and subtracting is really simple. So I'm just going to rub these out and we're going to do f times g. So if I want to do fx times gx, I'm going to need to use what we use for quadratics, where we're expanding brackets. So this is f times g. So when we were expanding binomials with quadratics, we use the FOIL method. The idea is that you have to multiply everything in the first bracket by everything in the second bracket. So the same thing happens here. It's just that there are more terms. So we have to multiply x cubed by everything in the second bracket. Then we have to do the same for the others. We have to multiply 2x squared by everything in the second bracket. And then the same for the third. We have to multiply 1 by everything in the second bracket. So that's what expansions do. We've done this before with just binomial expansions, which were easy. Now these are a little bit harder because there are more terms. So let's expand the first bracket. So x cubed times 2x to the power of 5. Remember our index laws. Keep the same base and add the powers when you're multiplying bases. So this is what happens when I expand the first bracket. When I expand the second bracket, minus 2 times 2, x squared times x to the power of 5, and so on. So now I'm going to collect like terms. So the first one, 2x to the power of 8, doesn't have any like terms. So I might find it easier if I do these in order and cross them out. So the next highest power here we have is minus 4x to the power of 7, which once again doesn't have any like terms. So there are no terms with a power of 6. Let's go to the terms with power of 5. So I have x to the power of 5 plus 2, x to the power of 5. So I get 3x to the power of 5. So now I look at the x to the power of 4 terms. There's only one of them, minus 2x to the power of 4. So then I've got my x cubed term, minus 9x cubed. And now I have some more like terms, 9x squared and x squared. Add them together to get 10x squared. And then we just have the minus 9 by itself. So that is very tedious. It is annoying, I understand, but we need to be able to do it. So when you're multiplying two polynomials, you just put them in brackets. Make sure you multiply everything in the first bracket by everything in the second bracket. So once again, we see the result is another polynomial. It has only a whole heap of numbers, and all the x's have non-negative powers. There's no fractional powers, no negative powers. So we've seen that adding two polynomials and subtracting two polynomials is easy. You get another polynomial. It's really quick to do. Multiplying two polynomials is kind of easy, but it takes a while. So you might be thinking, okay, what about division of polynomials? Well, that's actually very important, but very complicated. So much so, we're going to spend entire lessons on it. So for now, we're just going to do addition, subtraction, and multiplication. So the last thing we need to do is just some simple substitution. Please pause and copy this down if you need. So we've got our polynomial fx above. If I write the polynomial, say f2 That means I take my polynomial and I substitute x for 2. So f of 2 means x cubed minus 2 times x squared plus 1. And of course, that just gives me the number 1. So f of 2 gives me 1. I could substitute something else in. I could substitute f of a. So I would just change all the x's to a's. So everywhere you see an x, I write an a instead. I could be tricky and replace this with f of x plus 1. So that means I take my polynomial and everywhere you see an x, you write x plus 1 instead. So this one, if I wanted to evaluate it, I'd need to expand it. I won't do that here, that'll just take up more of your time. I think you get the picture. It's very important that we're familiar with this notation. All right, thank you so much for tuning in to this video. This has been the luckiest maths teacher in the world. Have a great day.